Hi, my name is Max Sullivan. Today we will be discussing Lesson 3 of Baking Pie from the University of Cambridge. If you have not yet seen Lesson 2, which you can find on my blog under Pie Videos, or under Pie Labs, I would suggest visiting it, as today we will be discussing Lesson 3, which is essentially Lesson 2. It does the same thing in both. We're looking to have a light on the Pi, the act light, flash. Now, Lesson 2 does this by just using a main.s file, and rather simplistically, no functions or anything like that. Today we will be using two files, which are gpio.s and main.s. Both can be found in the Solution Center on Baking Pie at University of Cambridge. They're given by Alex Chadwick. Now, what's important to realize in this lesson is that we're going to use functions rather than just simple coding. And why that's so important is theoretically we could go back in and we could change out the pin numbers and things like that in order to make the Pi do different things without having to recode the entire process and really messing with our main file. Now our main file, or without messing with our actual functions, we would only have to change in our main file the pin numbers that we're currently affecting. So let's go through and we'll review our code and then we'll build and I'll show you how it works. So we'll start out with our gpio.o, .s. It'll be .o once we build it. This is actually dealing with our functions. So here's where we're actually going to build our functions. This code is all posted on my blog beneath the video if you'd like to take a look at it for yourself. So the first thing that we're going to do is we're going to set a global function, and the reason it's important to make it global is so that way get GPIO address is acceptable to all files, not just here in GPIO, but when we call it later in main.s, we'll be able to access it as well. So our get GPIO doesn't have too much going on. Pretty much it just says let's create register R0 and pass it the following value. Then we want to copy that value from our loader right now into our program counter, so that way if we change it in the future or do anything with it, we don't destroy the value. And we'll be able to receive it again from our load register in the future. Then we'll come down here. Now we have another function, which is our global set GPIO function. Again, global, so that way it can be accessed from main.s. This function is actually going to be used to set the pins. Now, we did this in lesson 2 by just manually setting the pins in main.s. Here we're going to use a function that allows us to call this function with pin 16 that will flash light for us. So our first thing that we want to do is compare R0 with 53. There's only 54 GPIO pins, so the number can only be from 0 to 53. If it's any higher, it's outside of our range, and therefore it's not going to work. The program knows to just move down. Then if it's less than 53, and only if less than 53, it'll compare register R1 with 7. Now, and that's only because we have 8 functions per pin, so it'll be 0 to 7, and it only performs that again if R0 is less than 53. Otherwise, it just moves on. And it moves to here. It'll skip out if neither one of these are met. It'll skip out, and it says move if higher than back to the program counter and the load register. We then want to push the load register, which copies the value of the load register to the top of the stack if the conditions are met. So if both register R0 is between 0 and 53, and register R1 is between 0 and 7, we'll feel comfortable skipping this step and moving to push the load register. We'll then move the GPIO address from R0 to R2 to ensure it's not overwritten later in the program, and then just return GPIO address back when the function is called. So now we have our function loop. This first request compares R2, which now contains the contents of R0, to 9. If it is higher than 9, it now subtracts 10 from the pin number, because GPIO functions are stored in blocks of 10, as you can see up here, which will then allow us to figure out exactly where it is. So if it's higher than 9, we do the subtraction of 10, and then we add 4 to R0, and then we run this loop again. So that's just going to keep adding our register higher to essentially factor in the fact that we can only really compare R2 with 0 through 9. So it's going to say R2, if it's 11, for example, R1's going to move up one more, and now R2 is 2. It's going to skip both of these steps, and now you'll have R0 being 4 rather than 0, and R2 being 2 rather than 11, which allows the computer to actually comprehend the pin that you're calling for. Then we'll come down here. We want to add R2 to R2 and left shift it by 1. This is equivalent to multiplying R2 by 3. The left shift by 1, because we're dealing with binary and everything is done in multiples of 2, essentially, binary 1, 2, 4, 8, 16. It's by left shifting, it's equivalent to multiplying one of these numbers by 2 and then adding another R2 in addition, which is equivalent to multiplying by 3. We'll then left shift R1 by the value of R2, store the function back into the GPIO controller, and then pop the program counter, which returns the function. Next, we have set GPIO, and set GPIO will actually set the pin to allow the light to turn on and off on our Pi. So if we look at it, we have this is the first time we're actually going to rename registers to have a bit more of a comprehensive value. So this is done here. We're going to assign register R0 the name pinnum, which is an alias. Now, it's important to know that when we're done with these aliases, we have to release as is done here. We'll get to that in a second. It just makes it so that you don't accidentally use it. We're also going to give R1 pin val, and we're going to do a lot of what we did before. So you'll see, again, we're comparing the value of R0, which is now pin 1, to 53, with 54 GPIO pins. If it's higher, then we just return back to the program counter and load register. If not, we skip that, we pass that step, and push the load register. We then move the contents of R0 to R2, just as we did before, to ensure that the contents changed, and we can always get them back. And then we delete the name pinnum from R0. We then give that alias to R2, and R2 now contains the value of 4, which R0 still has. Then we return GPIO address, or we call the get GPIO address function from above here. And here. And now we give the alias R0 the alias GPIO address to reflect the function. We give R3 an alias pin bank, and we divide the pin number by 32. 2 to the 5th is 32. The reason that we do this is because these are only done in 4-byte increments. GPIO has two sets of 4-byte increments. At 30, one is 32 and one is 22. 4 bytes is equivalent to 32 bits, which is where we get the 2 to the 5th. We're then going to shift left the value in R3, which was loaded and stored here by this command, which divided pin number by 32. We then shift it to get it back into bytes, so we multiply it by 4. Or to get it into bits, I'm sorry. So we multiply by 4. GPIO address at this point now contains 202 followed by 5 trailing zeros if the pin number is 0 through 31, and this number if the pin number is 32 through 53. We then add GPIO address we now add the register, or the value of register R3 to GPIO address, which is register R0. And if that answer is 28 in base 10, the pin is on, and if it is 40 in base 10, the pin is off. And that's what's actually going to turn our light on. When the pin is set to off, the light is on. When the pin is set to on, the light is off. Rather the confusing thing that the Pi did, but you know what, we'll run with it. We can then get rid of the fact, or get rid of the alias pin bank, as we are currently done with it. So now we'll get the, we'll find a remainder for pin num divided by 32, as pin num should always be between 0 through 31. So remainder, it could be 64, for example. Once you find the remainder of it divided by 31, it's going to be 2, yes. So, because the first time you did division, or the first time you did it, it would be 2 with a remainder of 2, I'm sorry, which gives you the value between 0 and 31. We then give R3 an alias of set bit and pass R3 a value of 1. We then shift that bit, or that value, which is now 1, left by the value of pin num, which again is now that value between 0 and 31, thanks to this function here. We can then get rid of the alias pin num, as we'll no longer use it. Here we'll do a test if pin val is equal to 0. Now pin val is, I believe, R. It's named for R. Apologies. A bunch of these get jumbled sometimes. For R1. So pin val is equivalent to R1. So we test if R1 is equal to 0. And then we can delete the alias. If pin val is equal to 0, we store set bit 1, or set bit, which is equivalent to 1, at address 40, which again turns the pin off, as we saw using using one of the functions we used before. I'm sorry, I can't find it currently. We see, oh, it's right here. What a coincidence. So 40, pin is off. So if it's equivalent to 0, we store that 1 bit at 40 away from the GPIO address, which turns the pin off and the light goes on. If it's not equal, we store that value of 128 away from the GPIO address, which turns the pin on and the light off. Then we just get rid of our remaining aliases and pop our program counter, so that way we're back at the beginning. And now we will see how all of this affects our main.s file. So we have our main.s file, which really starts here. So we set the stack pointer to 8,000. And then we come down and we really start to use our functions. So you can see we're now giving giving pin num to R0. I'm going to start skipping these alias names. We're wasting, I'm sure, your time as well by just pointing all this out. R0 is now pin num. R1 is now pin function. We pass pin num a value of 16, which is the pin that turns the light on and off. I'm sorry. And we pass pin function a value of 1. We then call the set GPIO function and get rid of those two values. Set GPIO is again this function. This will check to make sure that R0, which is a value of 16, is between 0 and 53. It is. It will check to make sure that it'll check to make sure that 1 is between 0 and 7, which it is, and then it'll keep running, and it'll eventually get down to here, and run through. Now we will return back to here. So now we're running a loop. So we use our set GPIO function to set pin 16 to low, causing the LED light to turn on. So we run through all of this right there. And it's essentially set to 40 right now because this was a value of 1, which we saw. This is the set bit. And it passes the 40 away, turns the pin off, and the light. We now come into our loop. So we will do, we'll pass a couple more names as we just deleted them. So pin num will go back to R0. R1 will now take on the name pin val. Pin num will take on the value of 16. Pin val will take on the value of 0. We'll call set GPIO, which is once again, which is run here. And this is what actually starts to do the compares. So now we have it checks to make sure that pin num is between 53 or 0 and 53, and 16 is. So it'll skip the move high, move it higher. Call. It'll push the load register onto the stack. It'll move R2, the contents of R0, which is 16. Call get GPIO address. It keeps moving. It now compares. It checks to see if pin val is equal to 0. And again, if it is, it turns the light on. If it's not, it turns it off. So now we should have the light currently on as we set pin val to 0. That's right. So the light is not on because it checked to make sure here that pin val is equal to 0. Because it was, it moved at 40. The light goes on, and now we go into our actual on and off switching, which is done here. And that is done by saying that decrease is equal to R0, we pass R0 this value, which is just essentially a timer and starts to decrease. As soon as, if it's not yet equal to 0, we continue running the wait 1, which is this function. It just continually decreases by 1 until we hit. When we hit 0, we will skip out of that, and then I run this one, which now does the same thing, but now pin values past a 1, which means that once it goes into set GPIO, it'll do this function instead of this one, because when you test to make sure pin values equal to 0, this one has to be 1, and it'll turn it off. So, turn the pin on the light. And we'll keep doing that, so we'll just keep looping. It'll turn the light on by running this side, it'll turn the light off by running this half. Which we'll see in just a second when we load it into the Raspberry Pi. Again, I'm sure this is all a little confusing, just because we're moving back and forth so much between main.s and gpio.s. If you want to read the code, I think it's all commented out pretty well and pretty clearly. Again, just refer to my blog. So now we're just going to go ahead and build it for us. So we'll switch directories, and you've seen me do this before in my previous 2 videos. I maintain all of my source files and make files in my user. A lot of people split them between bin and user. Some people just have them in bin. Really up to you. So we'll clean what we currently have in there, because currently everything is done for us. So one of the things we had to do, because I'm using a Windows and not a Linux machine, was to actually kind of hack things up a bit. So before our makefile, it was running through, because now we're using 2 files, where before we just used 1. It was running through and it was building GPIO, and it was creating GPIO.o and putting it into the build file. And then it was moving down. And then it was doing it all over again for main.s and trying to build main.o, but the build file already existed and it was erroring out. And that's an issue with Windows versus Linux. So the way that we, or Unix, sorry, Linux, anyways, the way that we managed to kind of get around this was we were just going to build the directory ourselves, and so now it knows to go into the build directory, but it doesn't try to create another directory when we do main.s, because then those would conflict. You'd have 2 of the same name, and you just wouldn't get the right, you'd get an error. We can actually, I'll show you how that error works. So when we remove directory build, dir, see, we no longer have a build file. If we're on PyMake right now, so PyMake right now, we deleted build from our make file, so we're not creating the build file right now. It just airs out right there. If we were still creating the build file in our make folder, we would also error, but we would error on main.o instead, because build has already been created. Sure, you don't want to see all that. Just remember, if you're using a Windows machine like myself, sometimes it's easiest to just create the build folder from your make file and build it yourself. You know, not necessarily the most efficient way, but it will get the job done. So we'll go back and we'll make directory build. So now we have the build folder. You can see we have build in here. So when we run PyMake, everything has a place to go. We built it out. It ends the file. It builds main.o now as well. It calls both of those, builds a kernel image. Now we go dir, we have a build file, we have a kernel image that we didn't have before. I thankfully have already loaded that kernel image onto my Raspberry Pi SD card, which is right here. So that's already been pulled over from my Ugarto folder. If you're not sure where to find that, you can either refer to my other videos, or really quickly just It's just this image file here. I just copied it over. So now we'll remove our SD card, placing it inside of our Raspberry Pi, plugging in our Pi, and I'll show you the light flashing in just a second. So let me turn around the video camera. Now you're looking at me. Sorry, I was making such a face. And if you look right here, it's a little difficult to see thanks to our case, but you can kind of see a light flashing next to the red light. It's getting brighter on the case especially. So that's just showing exactly what Lesson 2 shows, actually, but a little bit more in depth. Video is much longer. Hope you enjoyed, and I think it's definitely worth taking a look at yourself. Thank you.